Hello, everyone. This is Professor Ma, and this is the short introductions on the sections on partial derivatives. Partial derivatives are at a point on a surface is the slope in the x-axis directions or the y-axis directions. Imagine you're on a surface of somewhere and you look in the x-axis directions. And if you were to walk along the surface, what will be the slope at that point? And once they are calculated quite easily by treating one of the variable as a constant and then do it the other way around. So you got different partial x, partial y. And then finally, what are these different direction in x direction slopes and on the y direction slopes is good for to measure this on a surface? Well, that's what we get into tangent plane and the or other kind of things. Okay, so here we go. So we have a surface of a functions and a piece of point on it, and we're going to set the b, y equal to b as a constant. Okay, and why y going to b? Oh, because that's a plane that's parallel to the x directions. So when I talk about the slope in the x directions, I'm talking about in this plane, the slope. And so if I take this intersection down to the xz plane, then I can see that this is in the plane y equal to b, and then the line have a slope. And how do I calculate that slope? I take the derivative of dz dx. Well, but in the equations, is what about the y? Well, y is a number of b. So that we say that's the partials, and we use these notations. Equal to at a p slope of the tangent at that point and in the x directions. Okay. And here's the limit definitions. Okay, you can think about that. And here's our calculator. Remember, we treat the y as a constant. So therefore, in every one of these expressions, think of y as your favorite number, say 5. So think of y as equal to 5. If y is 5, then how would you take the derivatives as, carry the number 5 around, or the symbol y? So first one, the derivative of y is 0. So a derivative of x is 1. The second one is 5 times x, so derivative of that is y, 5. And the third one, is 5 times x squared, so the 2 comes down, it's 2 times y times x to the first power, and so on. So, okay, so you can relate to this. Okay, and similar here, then we can find then the parametric line that's the tangent line at the point in the x directions. And how? We find the slope first. Okay, so you take the partial derivative with respect to x, so y, think of y as a constant. So to take the derivative of this, you can think of this as 49 minus x squared minus y squared to the half power. And I'm going to take the derivative of this. And this is constant, so it's only 1/2. Subtract 1/2, so this it brings down the expressions times derivatives of the inside, which minus 2x, and derivative of that is 0, that's minus 2x here. Then 2 and 2 cancels. So I get these versions, and then you plug in the numbers and you figure out that, oh, that slope is minus 1/3. So in these pictures, and that's the tangent line. And if its slope is minus 1/3, that means you step over 1, then the y or the z in this case drop by 1/3, minus 1/3. Okay, and this is important because from here, I can find the directions for the equation of the tangent line. Remember, the equation of this tangent line, we are talking about parametric equations. So I need a direction vector. The direction vectors is, this give me the direction vector, because if I were to put these vectors back into the standard positions, it will be in the y plane. This is in y plus 3. So in the 3 dimension, these direction vectors is 1, y 0, and z is minus 1. Okay. And that's the direction vectors. When I take the slope and realize the 3-dimensional version embedded in the plane, and then that's the directional vectors. Once I have a directional vector, then I can multiply by t, then add it to the point 2, 3, 6. Okay. The rest is easy. Okay. And so this is the parametric equation. Okay, we can do the same thing in the y direction, so I'm not going to belabor you. You can read it, except just that when we take the derivatives, we treat the x as a constant. Okay, and so this, and so think again, I'm thinking we, and the pi, these are finding partial z, partial x, partial z, partial y. So these are examples of, you can think of partial x, y is a constant. Partial z, partial y, partial derivative z, partial derivative y, x is a constant. Okay, so think about how these turn out. You can calculate, go through the derivative. And then here, then we can calculate then the concrete number, the slope in each directions on this surface, whatever it looks like. This is a point on this surface. Well, it should be noted. When I plug in x equal to 1 pi over 2 xy, z is going to be 0. Okay, I'm going to get z equal to 0. So this is a point on this surface. And so the number I get from here are the directions, the slope in that directions, x direction, these are slope in y directions. Okay. So that's the geometry. And now, in the partial derivatives doesn't tell the complete pictures on the surface. In one-dimensional, in one variable case, when the derivative exists, it means the curve is nice and smooth. I can have a tangent line. It doesn't have corners or something strange happens over there. The tangent from either side has to match. So it's smooth. The partial derivatives exist. However, partial x and partial y both exist. Do not guarantee the corresponding idea of what's a smooth surface. Okay, because if you think about it, if I'm standing on a surface, there are infinite many directions. In the case of a line in the pictures, there's only left and right. But on a surface, the 360 degree, everywhere there's 360 degree directions. And having partial x exists, like for instance, a fold like this, of this surface with fold in this picture. Let's think of sitting at the table, the fold. This, if you calculate the slope in either direction, if you are standing at the point P, it's flat in that direction, it's flat in that direction. So the slope is 0, equal to 0 for both. They exist. However, that's by no means a smooth point on the surface. Actually, it's kind of precarious. It's a point of a fold. Okay, so in order to differentiate what a smooth surface is, we need a condition. It turns out condition is the following. That is, you require the partial derivative to exist, partial x, partial y exists at a point P, not only at a point P, but also a small neighborhood, everybody around it, that their partial derivative can also be calculated exist. Okay, that's condition number one. And condition number two is not only the partial derivative exists, but they are also continuous. If both conditions satisfied, then we have a smooth, then we have the corresponding ideas of a smooth curve to a smooth surface. Okay, means no crease basically. Okay. And in particular, there's a theorem that's important, that is, these are different way of taking a higher partial derivative. I can take partial x twice, or can take partial x, then do it to y. And so we read this in this order. We'll do partial, this is partial fx first, then do it to y. Okay, so x comes first. That, and so on. And then there's a theorem that says, these are actually the same. Okay, provided again, around the point P, provided if the partial derivative exists around a small neighborhood around that, everywhere, and then the partial derivatives are continuous. If that condition satisfies around a small patch that's over at a point P, then the partial derivative at a point inside that small patch, you can switch the order, they will be equal. Okay, and this is true for most elementary functions. So for example, if I make a polynomial like that, and you can calculate these two, you can switch the order of taking partial derivatives, and you end up the same answer. Why? Because these are very nice functions, and its partial derivative exists around everywhere. Okay. And that's it. Okay, so this is the summary of the partial derivatives. And bye-bye.